Welcome back, everyone. I want to talk a bit more about numerical integration. Earlier in the course, we saw how to approximate the area under a curve using numerical integration. We talked about a couple techniques there, what we called the left endpoint rule and the right endpoint rule, and I have those formulas on the board for us to help us remember those. We've already seen how to use the left endpoint rule and the right endpoint rule to approximate our integrals. What I want to talk about next are a couple other methods we can use to approximate our integrals. And these other methods are going to be a little bit more accurate than our first two methods. Then we'll also talk a bit about controlling the error and making sure our approximations are good enough. Recall that when we were defining the definite integral and the Riemann sum that we used to approximate and find that, we started the process off by thinking about the area underneath our curve over some interval, usually from A to B, slicing that area or region up into a bunch of subintervals, and then we approximate the area of each of those subintervals with something like a rectangle. How we determine the height of the rectangle using either the left endpoint or right endpoint of each subinterval determines whether we're using a left endpoint approximation or a right endpoint approximation, but there's lots of other ways we could approximate the areas of these little subintervals or rectangles. We've seen that depending on the behavior of our function, like if it's an increasing or decreasing function, using a left endpoint approximation or a right endpoint approximation may give us an overestimate or an underestimate, just depending on the circumstances. And that's one of the nice things about using our first two techniques is we can sometimes tell right away whether it's going to be an overestimate or an underestimate, but these techniques are pretty basic and won't always be the most accurate way to approximate one of our integrals. So the next numerical integration technique I want to talk about is the midpoint rule. So as the name suggests in the midpoint rule, we're going to use the midpoint of each of our subintervals to help us determine the height of our approximating rectangle. So we denoted the left endpoint rule with L sub n and the right endpoint rule with R sub n. The L and the R let us know we're using a left or right endpoint approximation, and the little subscript of n tells us how many subintervals or subrectangles are going to be used in this approximation. Well, for the midpoint rule, we're going to denote that with M for midpoint and another subscript of n, just again telling us how many subintervals we are using in our approximation. So let me go ahead and write down our formula for the midpoint rule in both its sum and expanded form, and then I'll talk a little bit about what this notation means, because it is going to look a little bit different than our first two formulas. So for our midpoint rule, we have the sum from k equals 1 to n of f of x sub k over bar times delta x. Our delta x is the same as before, just b minus a over n, making sure all of our subintervals are of equal width. And we're multiplying that by this f of x sub k over bar, that's giving us the height of these approximating rectangles. And what this little x sub k over bar is denoting is just the average or the midpoint of each of our subintervals. So how do we find x sub k over bar for, say, this first subinterval? Well, we take those two endpoints, add them together and divide by 2, find their average or the x value that is right in the middle of those two. How do we find the midpoint for the second subinterval? Well, we take x1 and x2, add those together, divide by 2, and find their average or midpoint value. So in general, if we are looking in the kth subinterval, we're going to have to take the left endpoint of that subinterval, add that to the right endpoint of the subinterval, and divide it by 2. So it's going to look like x sub k minus 1 plus x sub k all over 2. And so we'll often look at multiple estimates for the same integral to help us get an idea of what the true value of that integral might be. Depending on the situation, maybe we know that the left endpoint is an underestimate and the right endpoint is an overestimate. Well, then maybe the midpoint will give us something in between those two, and that'll be closer to the true value of our integral. Another good way we could try to approximate or improve our approximations to try to find the true value of our integral, instead of using the midpoint rule, which uses our sample points as kind of the middle points between our left endpoint and right endpoint approximations, we could also just take the average between our left endpoint and right endpoint approximations. Right? And that makes a lot of sense, especially if we think about, well, if one is an underestimate and the other is an overestimate, if we add them together, take their average, it'll get us somewhere in between those two, and hopefully that'll be closer to the true value of the integral. Well, the next numerical integration technique or rule I want to talk about does just this. It does find really the average between the left endpoint and right endpoint approximations, and we call that one the trapezoidal rule. And so here I have our formula for the trapezoidal rule written up on our board. So just going over this notation real quickly, T sub n, T for the trapezoidal rule, n for how many subintervals or trapezoids we are using in our approximation. And it doesn't have a nice clean little summation formula that we can write for it. So we usually write it or express it in this expanded form. And so it's going to be 1/2 times f of x naught plus f of x1 plus f of x2 plus f of x3 and so on until we get to that second to last endpoint, f of x sub n minus 1. And then our final term in the sum is 1/2 of f of x sub n. Then of course we have to multiply that by delta x to finish it all off. And earlier I mentioned that this is just the average between the left endpoint rule and the right endpoint rule approximations, and we can actually verify that or prove that really quickly. And so to quickly prove the trapezoidal rule and its formula really is just the average between the left endpoint approximation and our right endpoint approximation, we can just, well, take the average between those and see that we get this exact same formula. So what we're going to look at over here is the left endpoint approximation, all those terms added to the terms from our right endpoint approximation, and divide that by 2. So let's go ahead and see what's going to happen. Well, we're going to have a lot of like terms here, right? F of x1 shows up in both sums, as does f of x2, f of x3, and so on until we get to f of x sub n minus 1. All these terms are going to be double counted when we add the left endpoint and right endpoint approximations together, except the very first term and the left endpoint approximation and the very last term and the right endpoint approximation. So we're adding all these up and then dividing by 2. So that first one, we're only going to have 1 f of x naught, but we have to divide that by 2. That's where our 1/2 of f of x naught comes from. Then we have 2 f of x1s that we add together, one from ln and one from rn, but we divide those by 2, and that leaves us just with a single f of x1. And well, we can see the same thing's going to happen here for our f of x2s. We don't actually write it here. It's included in those ellipses there. But we'll have 2 f of x2s, divide those by 2, and we just end up with 1 f of x2 in our formula, and keep going down all the way through the end. We double count the f of x sub n minus 1 term, and then we only have 1 f of x sub n term. And we have to divide that by 2, so we get 1/2 f of x sub n. That finishes off our sum of our terms. Then we have to multiply everything by delta x, the width of our rectangles or trapezoids. So this is a quick little proof to verify that the trapezoidal rule really is just the average between the left endpoint and right endpoint approximation. So that means if you've already found those two, you don't need to go through this process again. You can just add them together and divide by 2, and that would give you the estimate that we get when we use the trapezoidal rule. But I think the question that is maybe floating around out there is, why do we call it the trapezoidal rule? Well, the reason we call it the trapezoidal rule is instead of approximating the area of each of these subintervals using a rectangle, instead we approximate the area of each subinterval using a trapezoid instead. So let's go ahead and see how this all breaks down by looking at this last little subinterval, because I think that one most resembles a trapezoid. So here is the trapezoid we might use to approximate this final subinterval. Right, and already just from our little picture here, we can see how this might have some advantages over using just a left endpoint or right endpoint approximation. If we used a right endpoint approximation, then the top of our rectangle would be right here, and we'd add in a bunch of extra area that's going to cause a lot of air. And if we used a left endpoint approximation, then the height of our rectangle would be right about here, and then we'd be missing out on that area above our rectangle, which would also introduce some air in our approximation. By using this trapezoid, we are having less air involved in the approximation of each subinterval. But now the question is, how do we find the area of each of these trapezoids? And the way we do that is by decomposing it into 2 simpler shapes, finding the area of each of those simpler shapes, and then adding those areas back together. Well, what are the 2 shapes we break our trapezoid into? We break it into a rectangle, which we already know how to work with, and then we break it into this triangle on top. So now we just have to find the area of this rectangle and add to that the area of that triangle on top. And so our trapezoidal area is going to be the area of our rectangle, which is just going to be base times height. Its height, we could really use the left endpoint or right endpoint for. It doesn't matter as long as we're consistent throughout. The way the picture is drawn here, it looks like I'm using the left endpoint for the height of the rectangle, so let's stick with that. That'd be the height given by f of x sub n minus 1. Then we have to multiply that by the width of our rectangle, which is the width of all of our subintervals here, that quantity we call delta x. So remember, this first term is just finding the area of our rectangle. Now we have to add to that the area of the triangular piece on top. And how do you find the area of a triangle? Well, it's 1/2 base times height. Well, what is the height of our triangle and what is the base? Well, the base we know is going to be the width of our subinterval delta x. What we have to figure out now is what is the height of our triangle going to be? And so if we want to find the height of this little right triangle, we have to take that upper y value, which would be given by f of x sub n in this case, and subtract away from that the lower y value, which would be given by f of x sub n minus 1. Sorry, I got a little squish there. But the idea is now we could recreate this trapezoid formula for each and every subinterval. And what's going to happen is when we add all those up, we're going to get our formula that we saw before, right? Lots of these terms are going to be double counted, all of them except the far left and far right points. And for those far left and far right points that are not double counted, they have that factor of 1/2 coming from our area of a triangle formula. That's why we have those first and last terms in our trapezoidal rule formula. All right, so now that we have our midpoint rule and trapezoidal rule formulas, we're ready to look at some examples of applying these formulas and making some approximations. Welcome back, everyone. In this example, we are asked to approximate the definite integral from 2 to 4 of the function x squared using m4 and t4. That is our midpoint rule with n equals 4 and our trapezoidal rule with n equals 4. So let's go ahead and jump right in. First, we'll use our midpoint approximation with n equals 4. So remember, if we want to use our midpoint approximation, the first thing we're going to have to do is find the midpoint of each of our, in this case, 4 subintervals. And so we're approximating the definite integral from 2 to 4 of the function x squared, so we can interpret that graphically. So our function f of x, or y equals x squared, is going to look something like this, just our parabola that is concave up with a vertex at the origin. And our interval of interest is from x equals 2 to x equals 4. And so we could use that formula that I had in the last video to kind of just number crunch our midpoints, or we can think about it a little bit more conceptually. So what's going on here is we have our interval from 2 to 4. First, we want to split that into 4 equal subintervals. So we can first split our interval in half to make 2 subintervals. Then each of those subintervals can be split in half again to make our 4 equal subintervals. So now that we have our 4 subintervals, what we have to do is find the middle point of each of our 4 subintervals. So in our first subinterval, our middle point would be between 2 and 2.5. So that'd be 2.25. In our second subinterval, we'd have to find the midpoint between 2.5 and 3. That'll be 2.75. We do the same for our next 2 subintervals, and those midpoints will be 3.25 and 3.75 respectively. So let's go ahead and plug our values into our midpoint formula, and we're using n equals 4 here. So we're going to have 4 terms that we're adding together. The first one is going to be the value of our function at that first middle point. So that'll be the value of f at 2.25. We have to add to that the value of our function at the second middle point, which will be at 2.75. Then we add to that the value of our function at the third middle point, which will be 3.25. Our last term is going to be the value of our function at that last middle point. For our last subinterval, we found that to be 3.75. And then we have to multiply this by delta x, which is the width of each of our original subintervals. And so let's see, we can always use our b minus a over n formula. So that's going to be 4 minus 2 over 4, and that'll be 1/2. So I won't always write this next step down, but for this first example, I think it might be a good idea to do that just to remind us exactly what is going on here. So we're evaluating our function at x equals 2.25 for this first term. our function just squares its input. So that'll look like 2.25 squared. Our next term is just going to be 2.75 squared. Then our next two terms are going to be 3.25 squared and 3.75 squared. We add all those squared terms together and then multiply their sum by 1/2, and that'll give us our midpoint approximation with n equals 4. And if we plug that into our calculator and take the time to calculate that, what we end up with is 18.625. All right, so we have completed the first part of our example. We have found our midpoint approximation. Now to finish this example off, we have to find our trapezoidal approximation. So now to find our trapezoidal approximation with n equals 4 for subintervals for our same definite integral, we just use our formula that we still have written up on the board. And so what's a bit nicer about the trapezoidal rule is, well, we don't have to take the time to find all those little midpoints after we've created our original subintervals. We do have a couple extra terms, but I still think it's a little bit quicker than using the midpoint rule just because you don't have to find those actual midpoint values. So let's go ahead and plug everything in. So the first term in our sum is going to be 1/2 of f of x sub 0. F of x sub 0 is our far left endpoint for our original partition of our subinterval from 2 to 4, or our interval of integration from 2 to 4. So that first left endpoint, or x0, is going to be 2. So we're going to have to look at 1/2 of f of 2. We have to add to that f of x1, the right endpoint of our original first subinterval, and that'd be that yellow value of 2.5. So we have to add this f of 2.5. Next, we add on the next endpoint in our original subintervals, well, our function evaluated at that next endpoint. That'd be f of 3. Then we add to that f of 3.5. And now to finish off our trapezoidal rule approximation with n equals 4, we add in 1/2 of f of our last endpoint's x value. So that'll be 1/2 of f of our final endpoint was x equals 4. So it'll be 1/2 times f of 4. So we have to add all these together, but we can't forget that we have to multiply all these by the width of our trapezoids or rectangles, or however you want to view those regions, delta x. And our delta x is going to be the same as before, just 1/2 coming from b minus a over n, or 4 minus 2 over 4. And so now we can input all this into our calculator, and when we crunch these numbers, what we should find to be the value of our trapezoidal approximation with n equals 4 is 18.75. And so now we have two approximations for the same definite integral. The next question we might have is, well, which one of these is more accurate? Which one has less error? And well, since the definite integral I chose is one we could actually evaluate exactly using antiderivatives, we can actually answer this question right now. And we're going to go through this very, very quickly. So we're looking at the definite integral from 2 to 4 of x squared, evaluating this using the fundamental theorem of calculus. The first thing we need is an antiderivative for x squared, which is going to be 1/3 x cubed, just using our power rule for antiderivatives. We have to evaluate this at the upper limit of integration, which is going to give us 1/3 times 2 to the 4th. Then we have to subtract away from this our antiderivative evaluated at that lower limit of integration, which is going to give us 1/3 times 2 to the power of 3. Looks like I made a little typo there in that first term. That should be 4 to the power of 3, not 2 to the power of 4. All right, well, 4 to the power of 3 is 64, and if we multiply that by 1/3, we get 64 thirds. 2 to the power of 3 is 8, so that'll give us 8 thirds. 64 thirds minus 8 thirds is going to give us 56 thirds. And so 56 thirds is exactly 18.6 repeating. And so now we can see which of our approximations is an underestimate. It looks like our midpoint approximation was an underestimate in this example. And it also looks like our trapezoidal rule was an over approximation. And so what we could also do is find the error in each of these approximations just by looking at the difference between the true value of our integral and the approximate value of our integral, right? The error is just what you'd have to add to your approximation to go from your approximation to the true value. So here we'd have a positive error because we have to add a number to get up to 18.6 repeating. And here we'd have a negative error because this number is too big. We have to add a negative number to make it a little bit smaller to get down to our true value.